just say Jerome and Zhang joined. I think they're our organizers. We didn't introduce them, but I want to very briefly introduce Jerome. It's essentially a principal scientist from Nava lab in Europe, right? I think he's most famous for the DAS3R, this type of work so far. I think basically he and his team did this amazing work. I think Zhao is very well known in the field. Zhao is currently a professor from Princeton University for major in computer vision. So yeah, I think we have an amazing panel here. So as I said, we're going to try to answer some online questions. Already got quite some online questions here. The first question I think is very general. It's great. I think every person can probably share your opinions. They say, what do you think the most exciting research direction in the next 3 to 5 years relevant to digital twins? Let's see. Who wants to start first? I'm thinking one by one. Yeah. Okay, sure.
But, not so sure about digital twins, but I think for 3D computer vision in general, it's going to be the integration of, well, first of all, going large scale. So it's going to be the LLM model for 3D vision probably. And secondly, it's going to be the integration of 3D computer vision, 4D computer vision into LLMs and then achieving spatial AI because of that.
Yeah, well, I completely agree. I think there are very interesting questions regarding like whether like deep networks alone can solve large scale digital twin reconstruction. This kind of question, I think, are going to shape the near future of how 3D vision is integrated into LLMs. And 3D vision is, it's pretty much everything in my opinion. Like the world is 3D, and 3D vision, like geometry, semantics, everything is encompassed in this. So I think that's what would happen in the near future, and I think that's very exciting.
Thanks.
I can add that I think data will be very important for 3D reconstruction, and I think there's a lot of promise in synthetic data, especially synthetic data from simulation.
Thanks.
Yeah, I would say there will be more feed-forward architectures for every component that we talked about. Geometry, material, relatability, everything will, like optimization will slowly go away because it cannot keep up with like having priors. So I think there will be more feed-forward, and all of that requires synthetic data to train. So there will be a lot more synthetic data.
Yeah, then you need the data, right?
Yeah.
Yeah, I think the many models will evolve again thanks to the existence of synthetic training data and so on, so that they can respect like how the physical world works by like physics-based learning, right? So the learning knows physics and everything, so that we can have more plausible models, more accurate ones, and hopefully also more editable and usable assets as well.
Cool. Thanks.
My one-word answer to what's exciting in the next few years is always robotics. I think robotics is going to be exciting. Of course, it's relevant to digital twins. But related to just reconstruction, what I'm seeing is that there had been a lot of emphasis on trying to do 3D reconstruction without 3D supervision. But nowadays, it looks like the large reconstruction models is actually winning with Hunyuan 3D, Trellis, and Clay and follow-ups. I think it'll be interesting to see whether there's going to be a comeback with 3D reconstruction without too much 3D supervision. Because right now it's like just throwing a lot of data, curated data, and it seems to be winning. It'll be interesting questions to see whether that's actually going to be the case for the foreseeable future.
Thanks. Yep.
Yeah. Well, I'm certainly excited about seeing more functional digital twins. I think at the workshop we've seen like incredible work on surface reconstruction and relighting and from objects to scene level. But at some point then, for them to be truly useful beyond sort of like just the current class of use cases in graphics, they're going to have to be much more functional than that. and asking what on earth that even means. I mean, do you know, think about what a cross-section of the materials of a shoe looks like. And at the same time, there's like these incredible new data sources, you know, so if you ever go through an airport and use a CAT scan, you know, they've got like, you know, full 3D cross-sections of stuff that's readily available at this point. And, you know, when you start to interrogate data whilst looking at that 3D stuff, then that's a whole nother category of data. So, you know, as soon as we move away from the surface pixels to like true structure, then we can start to move to true predictive models, however they're encoded, be it classic methods or neural encoder decoder methods, but let's be excited about more functionality of digital twins.
Cool. Yeah, that all sounds great, actually. Yeah, kind of. Exactly. I think
We've got one hand in the audience for that.
Oh, please.
So related to your point, like my advisor asked me this question of how to make digital twins like functional, and so since I didn't know, I'll ask you since you guys so like the thing she asked me was like, how would we use digital twins for like performance evaluation of buildings, let's say lighting or thermal comfort or like HVAC systems and so on. So like what directions do you see are possible towards that?
Yeah, I mean, it's amazing when the need comes about. I don't know if you saw this quite famous video that did the rounds if you're into computational fluid dynamic simulations, which is a good example of a digital twin technique when you do have good geometry. And it was around COVID. And the sort of like the grabby headline was, open this one window, you know, in your office to save like 1,000 lives. Do you remember that headline? And the point is that the functionality of the digital twin to show the flow of air. You know, if you open the wrong window, actually it could stifle the flow of air, you know, just because of the way that turbulence works and pressure builds up. Open the right window and actually airflow can go. So the value of, in that case, you know, solving a very practical problem led to the clear value of a functional model where you could at least, you know, trust the sort of like the air and particles and whatever was necessary, you know, be it a sealed room, except when the window was open, etc. So I'd throw it back to you, which is like, what are the applications that are unlocked by solving the functional digital twin problem, right? And, you know, as scientists, often we like to collect a lot of those together, group them and go, oh, that's a whole new category of stuff. Now, as it is, we're talking about digital twins, so you go and talk to like people in other engineering disciplines, that's all they do all day is model stuff for their application domain, be it a bridge, a building, an electrical circuit, right, whatever it is. Like when we're doing circuit design for new classes, we use a digital twin, right, and we model it all the way down to the fluid flow of the electrons through the circuits. It's more a case of what do we mean when we say a functional model? We're kind of trying to operate at this macroscopic level of humans interacting, maybe it's a robotics task. So I'd start with like, what's the problem trying to actually be solved, and then the techniques of functional digital twins will fill in because that's how we do everything. Yeah.
I just want to quickly add there, I think we define digital twin have all the properties, right? Also including physical property and all these other metadata, for example. I think in another sentence, just like I completely agree with what Richard says, like the digital twin, you might not need, solve your application problem, you might not need all the property from the digital twin. But if we can really recover and build a solid, comprehensive digital twin, your problem should be able to be solved.
Okay, hi. In last 2 days, I have seen really many amazing talks on like egocentric vision. And as we are discussing these functional digital twins, I want to ask if you know if anyone is doing a research on where you use egocentric vision and you are just like, squeezing objects and like playing with them around to extract the physical properties of things and then to train a model based on these kind of interactions.
So based on force and pressure from humans interacting?
Yeah, because you have like a hand extracted from these, so you know like what hands are doing, so you can maybe from these kind of data extract some physical properties of objects.
Yeah, absolutely. We do have people working on this, but I can't talk about it, actually. Anybody else who can talk about this?
I would just like to maybe also add something. So I think like digital twin may be a potential like fantastic enabler for robotics. Because as long as you have basically the reality modeled in terms of like 3D materials, everything, then everything, I mean, basically robots exist in this space, kind of, right? Their intelligence. So not only you can train them in like simulation, but they need to understand the environment. And to me, basically, digital twin is kind of what robot perception is, in a sense. So my feeling is that in the near future, we will have like maybe an explosion of like in the robotics field.
Thank you. As anyone can speak about this, thank you.
Yeah. Thanks.
I want to sort of go back to this like a functionality, because it's something that I've been sort of thinking for like a long time. I've done works on trying to model functionality like implicitly, but never really explicitly. I think this notion of what is a functionality loss that's differentiable, I think is still elusive. So if I were to give a very lazy like solution to dealing with functionality, I believe there are a lot more varieties of shapes, geometry, than function and motion. I think for the functions, I think for each function, you probably have a word to describe it, a text, a word to describe the function. But I don't think you have a word to describe every single shape, 10 million shapes in Object versus Excel. So in that sense, I think that the variety or variation of functions and motions are actually much less compared to shapes, like geometry. So in that sense, I think my lazy solution would just have some kind of like function, like knowledge base, just kind of have templates, prototypes of functions and motions. And I think that's a good start. And then you can go from there. You can use them to evaluation, for generation, and to composition and everything. I think that would be my lazy solution to dealing with functionality.
Yeah, you know, ourselves into some other time. So just a commentation.
Just a comment that I really love the two-way discussions going on here. So this is being a panel discussion with all the audiences. Anyone, if you have any questions, also meanwhile thoughts, just ask for a mic or hand it to you. So all the questions we have right now is also just cross out for someone submitted through Google Form. But we absolutely love to new questions and anytime, point me out your mind. Yeah, so just continue. Yeah.
Meanwhile, I was thinking on this question.
Well, I can ask an online question here. It's also a general question. Why do you think creating 3D digital twin is actually very important? For what aspect you think is very important?
This is not a question from GPT or anything?
Someone wants to be.
Maybe too general, right? Actually, I think we all know why it's important. I think, yeah, I agree.
Well, you know, given it is obvious, I think we'll just state that the task of building digital twins is just our way as scientists and engineers of codifying what we think is important to represent about things in the world because we think they're useful. And we call that a digital twin. We could call it building representations of things in the world that we find useful. So far, what we find useful apparently is geometry and textures and relatable textures of that. We're now discovering that what we might find useful are other representations of things in the world, like what happens when you touch them or bend them or open them or other action words. So it's not a bad question, it's just it's a bit of a language game. The DTC is a shorthand for the things we find useful to represent so that we can use them.
So since I have the mic, I want to add some spice to the topic. That yeah, so since we all know here, we all talk about digital twin is important. Everybody has some thoughts that what it should go on. But why it is not so obvious that why it is not the hottest topic right now? Everybody can directly jump on it and work and get their the impact they like, right? So what do you think is actually currently the main challenges that actually need to be maybe unblocked, or maybe like we need to really work really hard on it, and then to really have maybe to become the very obvious thing, right? We don't even need to ask the question, why is 3D digital twin important? Because everyone will think it is obvious, right? So any thoughts on that?
Yeah, so I feel one reason is because generation is so hot and hyped right now. So, and in a way, because the progress is so fast, the bar is lower for generation. You have like a small text description and you generate an amazing asset. And it's like, you know, blows people away. While, you know, the bar for a high quality, you know, capture or digital twin is, you know, much higher. So it's just hard. So it's just not I guess, doesn't create hype just the same way. But I feel like the hype will die down from generation a little bit. And actually, many of the methods are very related, right? One way to generate 3D objects is to generate, you know, 4 or 8 views of them and then reconstruct a 3D object, right? So it's super related. So I think it may change. Anyone else?
Thank you.
I'm not panelist, but I just want to share the challenges. Can I share that? All right. I've been using Isaac Sim actually over 2 years and 8 months. And just speaking of the starter challenge, you need to have a very good GPU.
That's like that's really.
Yeah. I'm not even talking about any of the assets that you have to buy probably or create using either using like, you know, inverse rendering or I don't know, just buying a scanner, which is also very expensive. I'm just talking about just a starter GPU or a starter like workstation. You need a very high end, so it already excludes a lot of researchers. And I'm talking about the industrial side. So other things is like, I actually use the Isaac Sim for 60 pallet pose estimation. And I work at Toyota Material Handling. We have like infinite number of different types of pallet. So even though you use many types of pallet, your data does not get, you know, good accuracy for a task that is just as challenging as, you know, 60 pose estimation, right? So there's a lot of challenges. I mean, but speaking of the generation that you mentioned, there are now research that is doing actually, you know, like a stable diffusion for, you know, digital twins. Like we are actually integrating it already that in something like an Isaac Sim. But I think the barrier to entry is the highest challenge. I mean, how could we like make this more, you know, I'm not saying beginner friendly, but open to more computer vision researchers, or you know. And there's other challenge for digital twins. You just don't need like computer vision expertise. You also need like computer graphics, and there's a lot. Like I would say, the computer graphics people don't know much about computer vision and deep learning from my experience. I don't know about now. I'm talking about like 5 years or 6 years ago. But then at the other end, the computer vision experts usually don't know much about computer graphics, and not everyone who goes to computer, you know, CVPR goes to SIGGRAPH, so which they should. But there's a lot of like, you know, disperse. Thank you.
Yeah. For the first question, for your first concern, I just want to say that's why our media friends become rich, right? Yeah, Jensen always say you buy more and save more, actually. But yeah. But I think yeah, it's just yeah. We also use Isaac stuff. We also test. Yeah, we understand the pain point, actually. Yeah. But I think I want to say I feel actually for me, I can honestly I'm actually originally from computer graphics background. But actually, I'm now mostly working on the inverse problem, actually, more in the computer vision. So I feel the boundary between this is actually quite blurry. What do you say? Yeah, I think from my point of view. Yeah, I don't know whether anyone wants to share.
Yeah, I want to comment a little bit about the kind of the steep learning curve or the barrier from entry. I think it's partially due to the fact that many systems that you would need to, for example, perform like inverse optimizations and so on, these are not super user friendly, right? I mean, it's partly somewhat understandable because many of these are kind of little research projects, and they lack the documentation. they lack the compatibility, right? If you don't have the right operating system, if you don't have the right hardware, it just doesn't run, or it crash, right? So there is this challenge on the maintenance and documentation, basically the support level. I think things are becoming better slowly, but absolutely not at like a PyTorch level.
Yeah.
So that's one reason why, say, certain tools haven't become as user-friendly as they could have been. In terms of performance, yeah, that part I feel that just like running large machine learning models, right? It is indeed still hardware intensive, right? The hope is that, yeah, I mean, I'm not sure if you buy more, you save more. But once we get like more and more advanced hardware, the hope is that someday you can run these things with a mid-tier hardware, right? Not the very best. So basically, this type of task becomes more accessible. But on the other hand, I can always imagine people will always try to make use of the latest and the best. So the very biggest model might still very well require the latest hardware that are maybe just too expensive for the most. But hopefully, at least the more kind of average or mid-level models or pipelines becomes more accessible during time, over time.
Cool. Yeah. Thanks all for sharing. I want to ask actually an interesting question. I think we just talked about. I want to go back to the generation part and reconstruction part, because these are the two technology we always talk about when we create the 3D digital twin, right? You could generate the model nowadays. You could also do the reconstruction. We have LM. LM is essentially principle. It's a feed-forwarding reconstruction model. But we also have, like, for example, yeah, the recent very good like flow match or this kind of diffusion-based method can generate 3D model. I'm curious about your thinking. What do you see the trend for the future? How you feel like pros and cons for this kind of generation vs reconstruction for the digital twin creation?
I mean, there isn't one obvious trade-off. So when you do reconstruction by a generation and use something like backsets, for example, for the representation, generally you don't get something which you get a very good 3D structure, very good looking object, but it's not faithful to the image, not very faithful. So it's not exactly 3D reconstruction, it's image-inspired object generation, if you like, or some degree of that. So one challenge could be to try to make it as accurate as you would get with, say, reconstruction using a point map or a depth map, if that's what you want to do. So if you want to get is a very accurate representation of reality, that's probably not appropriate just yet. But it's very useful.
Oh yeah. Okay. Yeah. I mean, I think these are obviously related questions. I find it interesting to imagine that people working on generative models with the kind of GPU power they need there, and that is really the hot topic. So I can't believe that it's access to like a GTX or even like cloud-based computing at this point. On the other hand, what it can be is that the complexity that the methods that mostly have been demonstrated in this workshop are highly, highly complex methods. Like if you look at some of the pipelines to achieve the state-of-the-art, even takes like a recent work from an intern in our team, extending LRM into, I think it's LIRM, where we introduced the inverse rendering into the, the complexity of that framework, it's just insanely complex. I mean, I used to work in SLAM systems and they got very complex. The complexity actually just went up once it went into industry, and we really had to solve the problems to be able to build like SLAM systems, like so 6-DoF tracking systems that really work and don't break. It just got more and more complex, not less complex. And for our friends who are actually in Gen AI, really deploying Gen AI, I've got to tell you, it's not that, their model isn't a bit of PyTorch code like this. They have entire teams working on just how to train the models, let alone like looking after new generations of models. So I think what we've got is a separation of the fertile ground of where if you start with just a bit of flow matching code, And all you've got to do is find a new problem where if there is a data set, it goes from, some noise to the sample in the distribution, whatever that sample is. Well, that's kind of interesting because you can learn that as an undergraduate, pick up some PyTorch code, and suddenly you can have a text to image generation in about an hour. Yeah, imagine doing that 10 years ago. Remember, we had GANs. Do you remember GANs? How complicated GANs were? To train a GAN was sort of an art form. And now, with a bit of flow matching code, you can have something better than what was the state of the art. Training in seconds, frankly, for small data sets like MNIST. That's how simple the techniques have become now. Of course, to actually really get them to be good, they get much more complicated again. And this is a maturing field where people are using digital twins, so they actually want certain properties that really have to do the job. So I think that's the reason why we're seeing a slowdown in this field. It's you go to, I'm sure, aviation conferences, not everyone's talking about the Boeing 747 anymore, or the 777. They're talking about the new stuff. But everyone's still flying around in the Boeing 777, right? So I think that's one. And then two is there are now three clearly distinct problems, but they are, as a colleague says, related. So you've got the reconstruction problem, you've got the generation problem, and you've got the forecasting problem. And the forecasting problem is the generation problem conditioned on data from reality. So you do want it to be as faithful to reality as possible, but you are also generating outside of the manifold. And so much of our reconstruction techniques have focused on a very, very specific form of reconstruction and forecasting within the geometric and photometric space. And so again, when we look at what's going on in the hot new thing around video generation, the answer is actually the same problems, except they just handle effortlessly dynamical interaction between objects, fluids, separating bodies that go from being a piece of paper to being 10 pieces of paper. And it's how would we use our techniques? Get it into Blender and try and simulate a piece of paper being torn into shreds. Suddenly you've got 10 tech artists trying to do that, right? And yet, you can type that into an engine today and get a piece of paper that gets shredded in seconds, on your GPU. So what we've got is the techniques that are coming around for the conditioned, forecasting or forecasting problem and generation. These are better techniques. And it's because we are, our precious representations, our explicit representations that are really good for efficient applications where we need them today are not good for tomorrow. We know that. So I think that's the paradigm shift that we're going into. On the other hand, where does the data come from for training these models? To getting, it's back to these techniques. We've got to have some strong controls. We've got to have steering in the cost functions about what really is a 3D thing. And that comes from the traditional techniques and so on. So yeah, I think that's the yin and the yang here is that I've got data generation from these kind of older digital twins, but most of the people here are working also on generative AI techniques. And the conditioned or forecasting problem will get interesting for this community if we move on to more functionality and away from just geometry and photometric reconstruction.
Yeah, I agree. I think from my point of view, honestly, I thought about this problem many times. Finally, I tell myself it's basically, I think the reconstruction generation, these two things for me, it's more I have a linear weight somewhere. I can either go a little bit towards generation or maybe a little bit more towards reconstruction. It really depends on actually what the downstream stuff needs actually.
What is that? Steve.
So, excuse me. So transformer-based architectures have really blown up recently. I don't need to tell you that. Even for tasks that are, 3D reconstruction, things that you wouldn't necessarily think of as a sequence, which is where these models came from. So my question to you is, what do you think is the inherent strength of this particular representation that allows it to unlock some of this 3D understanding that other architectures didn't really have up until this point?
I mean, it's kind of misunderstanding. It's working. Okay. The transformers are for sequences. There's nothing in a transformer that says it has to be a sequence. It's just a set, isn't it?
Sure. I mean, yes, but
there you go.
The idea came from Steve. Right.
Yeah, props, but yeah, really. So that's it, right? So it's not a sequence necessarily, and so you visualize as a sequence when you draw the tokens in a slide because you have to put them somewhere. But In many cases, like in VGGT, they're not sequential in any meaningful way. They just maybe have some positional encoding for the image tokens, but it's not a sequence, it's an array in this case. When you do vecset, these are similar to 3D points in a point cloud. So they're just very flexible and very adaptable representations, so they work for that as well. I should also make a point that there is a big difference between the internal representation of the model. We don't really know how that represents 3D information or 4D information, and what you get out of the model, which is an explicit, say, point cloud, for example. I think this is a very important distinction, because trying to force internal representation of models to conform to our idea of what 3D is doomed for failure, I think. So it's much better to have this approach in which the internal representation is implicit, and then what you have is the ability of converting that through decoders into different views of that representation that you can interpret. That could be a point cloud, but it could also be some, let's say, SDF function or maybe something else you need. And then this implicit representation can then become more and more versatile, and it's going to be the target of regression by neural networks, which are more and more implicit as well, so easier also for people to learn and use. The end game here is that as long as you understand deep learning, which is actually kind of easy to learn, then you should be able also to do 3D computer vision, I think. And again, the shift is to put more attention to implicit representation and let that do its thing, essentially. It takes a leap of faith, but it's probably worth taking it.
To me, there is also another aspect, is that, of course, transformers have attention, and I think attention is really like crucial, basically, for 3D related tasks. Like you can think of attention as some form of matching, like soft matching. I think matching is basically at the heart, of the core of like all 3D geometry, 3D reconstruction, and so on and so forth. And like transformers are extremely good at matching, basically. Being like text tokens together or patches, or I mean, when we studied the induster, we kind of looked at the attentions in the decoder, and I mean, it's very clear. I think it's in the paper. Very clear that the decoder is essentially like matching, two images in some like soft manner, I would say, which is very different from explicit matching done in the past with key points and so on. But in the end, I mean, yeah, I don't think the same kind of outcome would be possible with like just a convolution architecture, right? People have tried to stack two images, for instance, together, feed it to a convolutional network, but this does not, like, this is really
it's possible.
Like unable to perform matching, to perform 3D reconstruction. So I'm actually looking forward to what will come next after transformers, because I'm pretty sure transformer is not the ultimate architecture. But I think it has to be some even more like some kind of generalization of attention in the end, which I'm not exactly sure what it should be.
Yeah, I'm not sure either, but I wish it was there. That would be nice. But I just wanted to add that I think it is right. So transformers can have a lot with matching, but it goes beyond that. So in VGGT, for example, if we put a single image as input, so there is no matching to be spoken of, we still get very good monocular reconstruction as well. So it's just a very flexible representation too. So it does matching plus a lot more, I think.
Yeah, so I just want to answer the question again in a practical point of view. So I work on the inverse rendering problem, and it's a yield pulse problem. So basically we train the CNN and try to predict the BIDF for geometry. And it's always a pain to train the model on synthetic and test the model on real. And it never generalizes very well. But after changing to transformer, no matter so it's single image BIDF reconstruction, or it's like the multi-view, sparse view reconstruction, it always generalizes quite well. So I don't know why that's the case, but so that's just we observe, yeah.
maybe to raise a question on top of that. So I think we have panelists talking about we need data sets, and also we see all different type of method, large reconstruction model. That's the variance use transformers. Now it looks like all the papers have using all the data sets on the public. People have access in 3D, and all the methods are using transformers. And now it looks like it has kind of crossed the road, but also plateau over there. So what's your thoughts? The next, do we need smarter data, better data set, larger data set, or we need better architectures? Figure out what is better way to have actually not incremental breakthrough, but actually big ones. Yep.
I would say that definitely there is room for scaling up VGGT I think is a good example. It's basically, if you ask me, like improve Duster in lots of aspects, pretty much all aspects. And there is still, I think, a lot of room for scaling up the training, the architecture, everything. But in the end, I think there's still this limitation that tokens, you can have so many tokens, right? At some point, the cost is still quadratic, and it, like large scale SFM, you cannot fit 1,000 images. Maybe you can, but at some point it's going to break. Yes. And I think there's definitely some improvement, I think, in the architecture has to be done. Like, we have to move on to more beyond transformer architecture, something that can scale to really large, or maybe even pixel-wise prediction. That's what I believe. Maybe we don't need patches, we just actually need pixels. I'm not really sure, but we are currently limited, I think, by the transformer architecture in a sense.
I've got a slightly different perspective, but I don't think it's very controversial. If you can get a human to provide the digital twin of the quality of the thing, given the reference images or whatever other reference data, then I think we can all agree here that there's no problem other than that where's the data set that can train a method to generate the sequence of tokens that human did, given the input conditioning that they had. At this point, as talking about whether it's doable is not the problem. The fact that very few people have attempted to just decode directly into Blender files, you can decode it sequentially, you can decode it all in one go using a flow matching distribution matching technique, right? There are many techniques now, right? And you can use transformers in that space, you can come up with your own method, whatever, it's just a distribution at the end of the day. It's not the problem, right? If you want to use those techniques, they will work if you've got a data set, right? And the fact that most of our ground truth would come from humans producing those assets, even for something, a digital twin of this space. Go talk to the people in Hollywood. How do they generate their assets? And they might have an army of tech artists, but they do it, and then they render it, and then you watch it in a film, and you go, well, that was good enough for that application. Or you talk to the people in aerospace, and you're like, well, how did you design that wing? And they show you their CAD program, and they're like, well, I trained with this stuff in university, and here's the prior knowledge I learned about. But at the end of the day, it's mouse clicks and a few commands and a few shortcut keys, and you have a new wing. And then they put it into their simulator, and they look at some numbers, and they go, oh, it has the right CFD on this, and they carry on, right? There's nothing there that is new. Beyond what GPT already does, actually. It's just another language. The question is there a data set to train on? Now, if we agree on that, then actually it's a question about where does the data set come from, right? And that doesn't mean that that's an easy problem. It can be how do we generate these data sets of millions of Blender creators to show how, given a reference image, they make a faithful reconstruction and or the digital twin and or whatever else. If on the other hand we introduce new constraints that are about, say, novel reconstructions in domains that are completely out of domain and actually by definition must be more sort of prior free, then you come back to the good old days of techniques that perhaps just have to work and be faithful to only the data. And the interesting thing is that given these current architectures, there may be a whole well of techniques for just classic reconstruction that are super faithful, way more efficient using feed-forward models once they're trained. But, you know, we're not looking at them anymore right now. You know, we're looking at these other techniques, so that's okay. But I would suggest where isn't it a data set problem? In fact, I was in another workshop today, and I was following his talk, and the last thing he said to a questioner from the audience, his answer was, well, yeah, you know, if only we could get a big enough data set, the problem would be solved. And that was it, and then he walked off, and, you know, and that was the end of that talk. And it was like, I wonder how many times that's been said at CVPR 2025. So my question back to everyone else is that really all it is? Because if that really is all it is, you know, if we take that seriously, then that doesn't mean the end of the research. It means, like, let's take that seriously. You know, let's not keep searching for, like, things that aren't necessary. Let's answer the questions that are necessary.
I guess everything comes down to whether you believe the beta lessons or not.
Yes. So I think, like, recently there's a surge of 3D data sets. There's Megascenes, which is huge. There's like InfiniGen, which is like basically can generate infinite training data almost. There is, I don't know, like 360, 1M. There's massive data sets which are appearing in the 3D vision world. But I don't think this is, like, to me, this is one thing, but I don't think this will solve the problem. Like transformers, I'm sorry, I'm going back to transformers, but they have some inherent limitations. For instance, we know that typically, like, when they are trained at a certain resolution, they are not able to generalize to different image resolution, right? Which definitely is something that's wrong. Right?
But let me interrupt, you're still thinking in pixels. What is the human doing who created that model that's inside of the massive data set before it got into that form that's, you know, the representation? They did mouse clicks and button presses, and they created that 3D model on screen using their actual human vision system looking at the screen, which is nothing like a whole image thing anyway. And they do that quite reliably, and they get paid good money for it. They're called tech artists, right? So my point is, see beyond the pixels and the transformer operating on pixels, and you have a completely different space of generative models, which is just a language, if you want to see it that way. The question simply to you, I put it to you, like, how does a human do it?
I mean, you still have pixels one way or another, right? The human
do you?
Yeah.
Do they?
Oh yeah.
Are you sure?
I mean, your eyes are basically cameras, right?
No, they're not.
Why not?
No, they're not, no. So you have like a foveated vision system, you have saccades, you look around and you see the detail, and you look at perspectives in a completely different way as a human. I mean, I don't know if you saw my talk this morning, but you definitely don't see pixels. So what you've got here is the simple question to answer, which is, how did humans build those millions of models without a gigantic transformer network that spans like megapixels? And the answer is, well, they're using tools. And those tools require them to operate keyboards and mice and have, you know, somewhat, you know, a screen about this far away that if you were to really measure it in terms of what they're actually seeing is nothing like what your cost function that's doing generative AI is using. So you can see it a different way, but what they do is they manipulate the model and they look for changes using a different kind of matching function as you talk about, which is perhaps more discriminative. But, you know, simply answer that question. How does a human with mouse clicks and keyboard presses and what they see on the screen produce a model from a reference image? Let's just go with from a single photo, you know, to the extent that it is metric. Some people are better or worse at it. You may have the answer to it, but I don't think the problem is a transformer network. I think it's that, you know, that sequence of what they're doing there comes like from a very different type of training, very different from what the training is being used today, where you go from entire models and try and generate a model in the sort of like the final distribution space.
If then you keep recall how artists play plus so that bit large, you get us.
Absolutely.
So
that's right. So that's my point. There's a new data set, which is the millions of models, but instead of them just being the models, they have how the artist created that model. And now we can ask the question, can a transformer learn to generate in that space? Well, we did a paper, scene script, that generates literally the underlying scene structure of rooms. And it's amazing what it kind of can do with like very little data. And by the way, the output space is tiny because you're going to push that through a different function, you know, to do the rendering. You're not relying on generation of pixels. You're just using, you know, very basic text generation. So when you start to do that, then you have a different space for solutions.
I mean, I talked about InfiniGen, and this is the same kind of thing, right? So, in my opinion, this is a completely different problem. And the way the human operator operates to create, like to basically given a photo to recreate a 3D model.
Mm-hmm.
I mean, yeah, I think our brain is definitely not a transformer, but yeah, I think we still have pixels as input, and the output is, I don't know, sequence of actions, something like that.
You could argue that humans, they have this built-in amazing spatial intelligence, and they have built a tool around that. The tools are human shape, right? And they can use the tool then to use their spatial intelligence to solve the problem. So, you know, spatial intelligence is the answer. Okay, that was probably lame, but you know what I mean.
I wanted to comment a little. So yeah, I totally agree. Like a lot of this, I mean, like a lot of things are just stuck on not having enough 3D data, and partly it's I would say a skill issue actually. Like entire vision community was for many years working on things that are totally different from like sitting down and figuring out how those Blender people do the Blender things, and nobody just wants to suddenly switch. like people would just say, "Oh, there's no data, we cannot do anything." But I think actually, so we had at Adobe several projects for generating procedural materials, and I would say this is slightly simpler than generating procedural full geometries with materials and everything. But yeah, I mean, if this cannot be solved, then the full 3D also cannot be solved. But I think it can be solved. It's like there's not enough data at all. Like you have like 2,000 procedurals, and you can augment them. It's still not enough, but you can. You can just keep iterating and bootstrapping, and at some point we go to a point where you can take an image of a material and generate the procedural graph that generates a similar material. And I think this can eventually. Eventually you can take a photo of a 3D object or scene and generate a procedural description of how you get that scene, how an artist would do it. It's kind of like a bootstrapping problem. Like you can't just ask, where is the data of millions of scenes like that? Well, no, here's 100 scraped from the internet that were free. What can you do? So I think that's the...
So I have a reaction about whether it is a transformer in the brain, because I feel like the same question can be asked about how LLMs do reasoning and do math problems better than way better than average human, right? Because you could say, well, before they could do that, they say probably it's not a transformer, but now you probably will say, well, it is a transformer that can do all these amazing things. So I'm not sure that wouldn't necessarily apply to spatial intelligence. So that's my reaction. And as sort of in terms of sort of the training data, I feel that there's, in principle, I think if you have enough data, a transformer can fit the data pretty well, can sort of approximate to a degree that's fairly impressive. There is the question about sort of whether you can get enough data efficiently. That's a practical problem in computer science without talking about cost. There's no computer science because it's all about whether the thing is tractable, in terms of computation or cost in terms of dollars. So I think that sort of, if you consider that question, then you have to sort of maybe think about whether there are sub-problems for which it's very efficient to generate a very large amount of data, and you can solve that sub-problem pretty well. So that will sort of lead to some different conclusions.
Richard? Yeah, so because I heard spatial intelligence, I just want to share something that I accidentally learned, that there seems to be some understanding of how humans perform navigation. This was Nobel Prize winning work from 2014 by John O'Keefe. So he actually discovered that actually human brain has this internal GPS system consisting of these different cells, place cells, grid cells, and border cells, head direction cells, speed cells. I think over time, people discover more and more cells that actually don't quite exactly know how they actually work together. So I don't feel that's just a transformer can explain how they actually work. Otherwise, it would be maybe too simple. And then there's also a very recent article from Nature that actually seemed to discover that when humans make decisions, actions, it's very similar to how humans navigate space. So in a sense, we also navigate actions as well. So I think it's actually maybe the first thing to learn is actually learn how humans do it. But then if you ask reach certain things that we may not have to learn how humans do it because the superintelligence may be something very, very different. So I think both are valid explorations. I just don't think there's a single model that's going to be the effective model. It's going to be new models being discovered, I'm pretty sure.
Okay. All right.
It's a very awesome discussion, really appreciate it. Yeah, I think this concludes our digital twin workshop. Thanks everybody for attending. Hopefully you all get something take away, and hopefully see you next time, next conference. Yeah, thank you everybody.